everyone. Today we'll talk about the solution to the problem count unguarded cells in the grid. There are multiple approaches to solving this problem. They are probably all based on a standard grid approach. So you're going to be having a two-dimensional array, you're going to be traversing it in some sort of breadth-first fashion, and in this case it's even more constrained because you're probably going to be traversing it up, down, left, right, but without changing direction once you choose a direction. And in my opinion, the easiest way of solving this problem is to come up with a simple observation. And that observation is that we can actually, after marking all the walls and all the guards on our grid, what we can do is we can start at every guard and simply go up, down, left or right, marking all the tiles as visited, because of course he sees those tiles. And the only thing that we have to do is, of course, stop at walls, that's obvious, and stop at other guards. And you might notice that, for instance, cells between those two guards will be marked as visited twice. That's not really a problem, but what about time complexity? What about this tile? If this tile is marked not once, but twice, then how many times actually a tile can be marked is a good question. Because if we just go over the same tile many times, then our complexity will be bad. We probably want to have a complexity that's about m times n. But luckily for us, since guards only see things in 4 directions, when we look at a single tile, then obviously it can be seen only from 4 directions. From above, from below, from the left and from the right. And since we stop at the first guard that we see in every direction, if it's seen from above, some guard sees it. Same from the right, from the left, and from below. So it will be seen by those guards, it will be reached by those guards, and nothing more. Or maybe another thing for us to look at is that if we have a tile, how many times do we visit that tile? Well, maybe we visit that tile going upwards. That means that we visit it from some guard below it. And there is no more opportunity for us to visit this tile going upwards from anywhere. Because if a guard was above, that means that this guard will not have visited this cell. If the guard was below, likewise it will have stopped on this guard, it won't reach this cell. We have 4 directions, so for every direction the tile can be visited at most once. Which means that all the tiles can be visited at most 4 times, so it's still 4 times m times n. So this is indeed the time complexity is sufficient for us. And for the implementation we have to generate the directions, up, down, left, right. The order doesn't matter. We have to mark the grid, so we start with, let's say, 0s to mark empty tiles. And now all the tiles that have a guard or a wall are occupied, and they are occupied in the way that they block sight. This is opposed to tiles that are already seen. This is, of course, like we have a guard here, we have a guard here. Now, the guard is looking upward, so this tile is already seen. But we have to make sure that when we are looking left from this guard, maybe this tile is empty, this tile is empty, and we see this occupied tile, but we have to ignore it and we have to go further because maybe those tiles are empty and they should be visited. We only stop at a guard or at a wall. So we'll be marking them as negative ones. Whatever we want, just different than this one. And we of course mark both guards and walls, so for the list in guards walls, for row column in list, we mark it as 1. And now for the changes in directions, so change in row, change in column, and for every starting position in guards, we go in that direction. Here I'm showcasing the walrus operator. We can write stuff like this, row equals row plus difference in row, and immediately see if it's between 0 and height. Same for column and 0 and width. This is a standard way of writing it, although not with this kind of operator. And now if the site is blocked, we break. Otherwise we mark the tile as seen. Maybe it was already seen, maybe it wasn't, doesn't matter, we mark it as seen. And the final result is the sum over all the tiles that remain 0 at the end of the operation, because they were not seen by anything, and of course there is nothing blocking them. A question for you maybe, if you are not familiar with this operator, what would happen if we were to swap the order of those two loops? So why is the order like this? Because in general it doesn't really matter what the order is. will be doing the same thing. Maybe it will be executed differently, but the result will be probably the same. But not if we use this operator, so you might think about what happens if we swap the order.